Hi, and welcome to this biomechanical analysis of the running long jump presentation. My name is Yusuf, and I will be breaking down my own performance across each phase of the long jump, the running long jump, and identifying biomechanical faults, applying evidence-based corrections supported by the literature. By the end of this presentation, I'll have demonstrated how mechanical efficiency, particularly through approach, velocity, takeoff angle, trunk alignment, and arm coordination, impacts the distance achieved in the jump. So when determining what to observe during the running long jump, first we must cover the goal, the biomechanical goal. So it's to maximize the horizontal displacement of the center of mass while maintaining sufficient vertical lift for optimal flight time, according to Linthorne 2008 and Schiefer 2011. To achieve this, the athlete must effectively convert the linear momentum generated during the approach into a combination of horizontal and vertical takeoff velocity while minimizing energy losses through braking or instability. For this analysis, I identified four critical features. So the horizontal approach velocity and takeoff angle, the upright trunk alignment, and coordinated arm swing. These features were selected because they play important roles in manipulating force vectors and angular momentum throughout the jump. The deterministic model, which was developed on the next slide, shows how each of these interact to produce the overall goal, which is to maximize horizontal displacement. So the deterministic model was adapted from Gunther 1989, Schiefer and Gunther 2011, to illustrate the causal hierarchy of performance variables. So at the very top is the performance outcome, followed by the jump distance, which is determined by the takeoff velocity, takeoff angle, and aerodynamic control during flight. These outcomes are influenced by approach velocity, leg power, and arm swing synchronization. So each of which is underpinned by the athlete's neuromuscular coordination, postural control, and kinematic consistency. So the model highlights that the long jump is a multifactorial skill, so where the efficiency of one variable directly affects the magnitude of another, particularly the conversion of horizontal to vertical momentum during takeoff. So if one step fails, then the next step will not be as effective. So when observing the performance, my jump was recorded in the sagittal plane at 30 frames per second, and I used Canovia for motion analysis. It was recommended by Kaw and colleagues 2017 that marker placement should be applied to key anatomical landmarks, those being the ankle, knee, hip, shoulder, and elbow, to track joint angles, center of mass trajectory, and angular displacement throughout each phase better. I divided my analysis into key phases of the running long jump, the approach, penultimate stride, takeoff, flight, and landing. You can see on the next slide the key landmarks on my body. So moving on to observing the performance, the horizontal approach velocity. So it's the foundation of jump performance. According to Hay, Miller, and Canterna 1986, elite male athletes typically achieve approach velocities between 10 and 10.5 meters per second. In my performance, my velocity was approximately 0.9 meters per second, so indicating a substantial discrepancy, but also consistent effort across attempts. Biomechanically, this reduced velocity likely limited the impulse generated during the final stride. I observed a braking phase caused by overstriding into the takeoff board where the foot struck too far ahead of the center of mass. This anterior placement increased ground reaction time but produced a counterproductive braking force that dissipated forward momentum. That's from Linthorne and Guzman 2005 and Ramey 1983. So improving the stride rhythm and ensuring foot placement beneath the center of mass in the final two steps will allow for greater momentum preservation and kinetic efficiency at takeoff. The takeoff angle represents the relationship between vertical and horizontal velocity vectors. So research by Linthorne and Guzman 2005 shows that the optimal range for elite jumpers is approximately 18 to 22 degrees, which provides an ideal ratio between lift and forward projection. My takeoff angles were roughly 58 to 70 degrees, so far exceeding that optimal window. This over-rotation of the trunk resulted in excessive vertical lift and inefficient force application vector. Ramey 1983 states, excessive vertical impulse disrupts momentum transfer and increases flight apex at the expense of horizontal displacement. So this suggests that premature hip flexion and an increased moment arm between the center of mass and takeoff foot produces unwanted torque around the pelvis. The goal moving forward is to reduce this angle closer to 20 degrees by maintaining forward projection of the center of mass and reducing knee flexion during the takeoff phase. Moving on to the upright trunk alignment, the upright trunk alignment at takeoff stabilizes the center of mass projection angle and ensures efficient force vector summation. In my footage, I observed a slight forward trunk lean at board contact. This likely caused an overemphasis of the vertical lift during takeoff and limited my horizontal drive. When the trunk remains slightly forward, the hip extensors engage earlier, which may aid balance but also restricts angular velocity through the kinetic chain. Ko and colleagues highlight that the trunk should remain upright with minimal anterior tilt to prevent unnecessary rotational torque around the hip joint. Correcting this through core stability and hip extension coordination drills will help maintain a neutral spine and promote efficient energy transfer from lower limbs to the center of mass. The coordinated arm swing, the final critical feature, acts as both a stabilizer and a propulsive mechanism during takeoff. Lees, Graham, Smith, and Fowler 2004 found that a synchronous double arm drive contributes to up to 10% of total takeoff velocity by increasing the vertical component of angular momentum. In my own performance, my arm showed strong posterior extension, which is good for storing potential angular momentum, but was slightly asynchronous in their forward phase. So the right arm lagged behind the left, creating a small rotational imbalance that disrupted my center of mass stability during takeoff. This observation aligns closely with Lees and colleagues' study, which reported that even minor arm-leg desynchronization can reduce the total resultant takeoff vector. So moving on to detecting faults and weaknesses. So issue 1 was excessive takeoff angle. Number 2, insufficient low horizontal approach velocity, poor coordination between arms and legs during takeoff, instability of trunk in excess of forward lean during the final stride, and lack of knowledge around flight mechanics. So correction of these issues going forward, so simply to reduce takeoff angle, I'll implement plyometric training, specifically bounding and drop jumps to improve the rate of force development and enhance takeoff mechanics. To improve approach velocity, I'll perform maximal sprint drills and rhythm-focused run-ups to refine stride patterning and ground contact efficiency. Arm coordination, Matsui and Azuma 2021 recommend self-analysis using strobe imagery to enhance temporal awareness and improve limb synchrony. Trunk stability, Takahashi and Wakahara 2019 highlight the importance of core strengthening and proprioceptive control, which supports spinal alignment during each propulsion. So in conclusion, my biomechanical analysis of the running long jump revealed that my performance was limited by inefficiencies in approach velocity, takeoff angle, and arm-leg synchronization. However, through detailed kinematic and kinetic observations supported by peer-reviewed research, I managed to develop a targeted correction plan designed to refine my technique and improve energy transfer efficiency. While this analysis has not only enhanced my technical understanding of the running long jump, it's also demonstrated how applied biomechanics can translate into meaningful performance improvements. Thank you for listening, and I hope you have a good rest of your day.